we left off, we were talking about standard state enthalpy. So when we're talking about these thermochemical equations, we will show. Okay, so let's see. Take a step back. So when we're talking about these thermal equations, we're going to show it in terms of, in the case of standard state or standard enthalpy of formation. So standard enthalpy of formation is basically where you take the elements and then you're going to be generating a compound. So for instance, for carbon dioxide, let's see, hold on, let me let people in. And George, I'm going to give you co-hosting power so you can let people in.
Alrighty then.
Okay. So, because I'll leave them outside and they'll be waiting for hours by the time I realize that they. Okay. So, as I was saying, we take these elements, the pure elements, and then we basically use them to sit there and generate our compound that we're interested in. And so there's enthalpies that are associated with this that have been tabulated over time. And so I'll show you exactly where they're located in the back of the book here in a second. Make sure I have that available. And okay, so in the case of carbon dioxide, we have carbon and oxygen gas will come together to make carbon dioxide. And the enthalpy of formation, and that's just written with the degree sign and F, so delta H degree F, and that's enthalpy of formation. And that's going to also be equal to the standard enthalpy at 298 Kelvin. And again, this guy is actually kilograms per mole. Okay, because it's based upon 1 mole of substance, of pure substance. So, okay. Okay. So, can you guys write the heat of formation for the reaction of ethanol? So the formation of ethanol and the formation of calcium phosphate. Okay, so for ethanol, so what are going to be our reactants?
Carbon, hydrogen, and oxygen.
So we're going to have carbon, hydrogen. What is the chemical formula for hydrogen?
H2.
H2.
Okay. And for oxygen?
O2.
And that's going to yield our methanol.
Yeah.
I mean ethanol, not methanol. Okay. So is it balanced?
No.
Okay, what do we need to do to balance it?
I first see what you have on each side. So you need a 2 on the reactant side for carbon.
Okay.
And then you need a 3 in front of the H2 because there's 6 on the product.
Okay.
And then, oh, hold on. Let me do it real quick over here.
Okay.
I was trying to do it just like that.
We can multiply the product by 2 since we're putting in O2 gas.
We can multiply by 2.
The product, so 2 on the product side.
So, but I want the product to be based upon just a single mole of our product, because that's what we're looking at, that substance. So if I wanted to do that, what would have to be in front of the oxygen?
1/2.
Would be a half. Yes.
Oh yeah, I forgot about this.
Okay. Now what about B?
Ca
Plus phosphate.
Ca plus
P4
P4. Why P4?
is the
It's polyatomic.
It's polyatomic. That's right. And
O2.
oops. Okay, is that balanced?
Not yet.
Okay, what do I need to do to balance it?
3 on Ca reactant.
Okay.
Then 1/2 P4. Then 4 on O2.
Okay, piece of cake.
Yep.
Okay. Okay, so now we finally get to Hess's law. Hess's law basically says that, remember when we talked about it doesn't matter which way you go, so you can take a long little path, as long as you get to where you're going, right? So Hess's law basically is going to say that as well. So we have the option of taking multiple little reactions and putting them together to get our final product. Or we have the option of just doing the reaction directly, right? So the way that heat is determined, there's 2 ways. One is done by experimental, so experimentally, that's what you guys did the other day when you guys were in lab. Or you can sit there and use calculations that were derived from somebody else's experiment. And so again, we have tons and tons and tons of heat formations of various chemical compounds. And if you guys actually take a look, in appendix in your textbook, in appendix G, so in appendix G, you have your delta H of formation. And so the way it works is that you're forming these particular compounds. So for instance, if you're going from, let's say, aluminum solid to aluminum gas, it takes an enthalpy of 324.4 kilojoules per mole. Okay. And so you would write that chemical equation as if you're going from, in this case, AS ALS to AL gas.
Mm.
And that's going to be your delta H, the formation is going to equal okay, piece of cake.
Yeah.
If we're doing something more complex, let's say aluminum sulfide, we'd break it down to its elements. So we know that aluminum is just the metal itself. And then we have sulfide. Now, sulfur, what is the chemical formula for sulfur?
S8.
S8.
Good. Okay. And then that's going to yield so how do we balance this?
We need 2 aluminum.
Okay, so we need 2 aluminum. And how many sulfur?
Just 3, so it'd be 3/8.
Piece of cake. And then our enthalpy would be whatever that value is, which is negative 724. Okay. Good so far? Okay. Let's see, clear. Okay. So sometimes we'll run into reactions that are going to be difficult to understand or to measure. And so that's when being able to sit there and add up the sum of reactants of your different reactions will make it a lot easier to sit there and do the calculation. Not too far. There you go. Okay, so HESS'S law is also going to be a state function as well. And basically the state function just says that we can add it up to sit there and get there, or we can go there directly. Okay, so for example, if we were going to look at the production of carbon dioxide, so we can go there directly by just using the heat of formation of carbon and oxygen to make carbon dioxide, or we can do a two-stepper. So first we make carbon monoxide. So we have carbon plus 1/2 oxygen gas yields carbon monoxide. And that's the enthalpy that's associated with that. Then step 2 is that we have carbon monoxide plus 1/2 oxygen gas to make carbon dioxide. And so in this case, we'd add the sum of both of the chemical equations. And so you guys see we'll have carbon, 1/2 oxygen, carbon monoxide, another 1/2 of oxygen. And then on the product side, we have carbon monoxide and carbon dioxide. Now, anytime that you have a chemical on both sides of the chemical equation that are exactly the same, they cancel out like spectators. Remember that? And so the net reaction is just going to be carbon plus, we have a 1/2 here, 1/2 here, so that adds up to 1 whole oxygen gas, and that's going to yield carbon dioxide. So In that case, we'd also have to add both of the enthalpies together. So then the delta H for this guy would be the sum of the two, which would be negative 394 kJ per mole. Piece of cake? Okay, good. Okay, and this slide just basically tells you what I just told you. Okay, questions, concerns, Cash? Good. Okay, so here, this is just basically showing you what we just talked about in a diagram. So we have the option of going directly to carbon dioxide, so that's just by the heat of formation, or we could break it down into two independent equations, but it gets to the same point. Okay. So, to use the heat of formation, we could actually use the heat of formation to sit there and do reactants of various types. So very complex reactions and things like that. So for instance, let's see. The way that we would do that is that we would take the sum of the products times the number of moles minus the sum of the reactants times the number of moles. So let me just show you the equation. Oops. Okay. So the sum of the products minus the sum of the reactants, okay, of their enthalpy. And we have to multiply them by the number of moles because it's based upon that molar ratio of the chemical equation. So for instance, let's see, come on. Okay, so here's the chemical equation that we're interested in calculating. So although this one isn't on our table, this guy is not on our table. This is the heat of enthalpy for it. So if you take a look, we multiply the number of moles or the coefficient times the enthalpy that's associated with that particular product. Okay. And then we add that to the number of moles times the enthalpy associated with the carbon monoxide. And then we subtract our reactants. So the number of moles times the enthalpy of nitrogen dioxide, and then the number of moles of water times the enthalpy of water in this liquid form. Pretty simple. Okay, so let's see. Let me think of a chemical equation here. Let's do Well, let's do this. Okay, so let's do this equation here. Okay, so you want to look on your table, see if you can find your elements. H, C, 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 H. I only have HCl. So let's do it like this then. We'll make this aqueous, we'll make it gaseous. And then we'll have to use gaseous water to make that happen. Okay. So okay, so if I'm doing my calculations, what am I going to do? Let's see. What am I going to use to calculate the enthalpy?
Products and your reactants?
Okay, so my products,
Yeah. HCl is negative 92.307.
okay. So then we have okay, we're going to multiply that by
2.
okay.
Wait, where'd you get the 92,307?
Right here.
Oh, okay.
Okay. And then oxygen gas, I believe is 0. Oops, wrong way. Oxygen gas, 0. So, and then water, because chlorine gas is 0. So we minus our water, which I believe is negative 2.42. So how many waters?
Just one.
1. Okay. So 1 mole times negative 241.82 kJ per mole. And what did you get for your delta H? Oops.
I got 57.206.
Point.
That's what I did wrong.
Okay. Oops. Okay, so. And then that will be it. Piece of cake?
How do you know if the answer is like negative or positive?
You should pay attention to the sign in that case. And then also, if the answer is a positive number, then that means it's an endothermic reaction. That means that overall, the reaction had to put energy in to make it happen. Or if it's a negative number, it should be an exothermic reaction. That means that you're going to get heat being generated.
Okay.
Okay? Does that help?
Yeah. But what about the chart? Wait, can you like scroll up?
Yeah.
Like I was just confused on like when you were getting the numbers. Oh, it's for the delta H.
That's right.
Okay. Because I don't know what the other stuff was.
Yeah, we haven't gone over it yet. That's second semester.
Oh, okay.
Yeah. So this is Gibbs free energy, and then this is enthalpy.
Oh, okay.
We'll talk about that. Don't worry. Then you're going to want to throw things at me at that point. Okay. Questions, concerns, Cash. Okay. So you guys have just completed chapter 5. We're going to start chapter 6. Chapter 6. Chapter 9. So we're going to skip over 6, 7, 8, and then we're going to go directly to 9. Then we'll come back to 6, 7, and 8. Okay?
Sounds good.
Okay. So we're actually going to stop at this point. Are there any questions? I didn't think it was only going to take 30 minutes. Because I don't want you guys to be too far ahead of the other class because they have a holiday next week.
I have a question.
Yes.
Where can I find this chart? Because I checked my online book and it's not there.
Are you sure?
I'm pretty sure.
Okay. So you can actually find it in the appendix G. So if you click on the table of contents in your PDF or your online book, click to appendix G and it'll actually take you directly to it.
Okay.
Or if you just download, because the book is also on Canvas, you can download it from there.
It's because on the table of contents, it doesn't show the appendix. It just shows index.
How much you want to put money on that?
Want me to share my screen?
Yeah, you can share your screen.
Okay.
Here,
good.
let me stop sharing mine. And then you can share yours.
Okay, give me 1 second.
Put money on it.
What was that?
Put money on it.
Okay, you want to put money? I'm down.
I'm good.
Okay, let me see. Am I? I don't know. I should be sharing already. Am I sharing?
Yeah.
Mhm.
Okay. This is my table of contents. It's down here. This is the last thing on my
Wow.
this index.
Okay. So.
Oh, it's right here. Right?
Yeah, it is, huh?
It doesn't say appendix. That's why.
Okay.
But I was like, why is there letters? Okay, never mind. How do I stop sharing?
Man, I just earned some quick cash.
No, you guys didn't. You guys didn't want to.
Damn it.